Let's start with current of electricity. After we're talking about the electrons in the past chapter, now we will talk about the movement of the charge. When a charge starts to move through a wire, so we have a current. Current is charge per unit time or rate of movement of charge per unit time. What's move inside the wire? We have here the negative and positive sides of the power supply or battery. We have here, maybe we have a bulb. Now, the electrons will move from the negative side to positive side outside the battery, and from positive to negative side inside the battery. This is the electrical current. Okay, now we will use the conventional current, which is the movement of positive charges from positive to negative outside the battery and from negative to positive inside, which is the conventional current. Okay, we will use this current because it is known before knowing the movement of the electrons. We have electrons which is move in a wire, and if we have water solution like salt with water, the ions will start to move through the material. Okay, so the electrons or ions can move through the material to allow the current to pass. This is known as the electrical current. Electrical current I equals Q over T. It is coulomb per second, which is measured using unit ampere, and we use a meter to measure the value of current. Now, the atom consists of a nucleus, and the electrons are outside the nucleus. Inside the nucleus we have protons and the neutrons, and the electrons outside. Because of that, the electrons can transfer from one place to another. The definition of Coulomb, it is the charge passing a point in a circuit when there is a current of 1 ampere for 1 second. So Q equals IT. The conventional current, as I mentioned before, it is the movement of the positive charges. Okay, it's the flow of positive charges inside the wire. We will use the conventional current through all this syllabus and other syllabuses. They use this current. So we know that I equals Q over T, which is charge per unit time, and the charge is number of electrons multiplied by charge of electron over time. This is another law for current. Now, we want to find a relation between the current and the area of this wire. We take the wire, this is the cross-sectional area of the wire, this is the length of the wire. Okay, the electrons will move in this direction, the positive charge will move in the opposite direction as well. Now, we will define a new symbol, which is capital N, which is the number of charges per unit volume. Okay, this is volume. Now, so instead of N, I can write this I equal capital N, which is the number of electrons multiplied by volume. Okay, or this is the number of electrons density. Okay, multiplied by volume by charge of electron over time. Okay, and using the law of the volume, which is area multiplied by length. So we have N, which is the charge density, multiplied by area length, charge over time. Now, length over time, which is distance over time, it is speed. So current equal N A V multiplied by Q. Q is the charge of electron, V is the drift speed, A cross-sectional area, and N is the charge density, okay? It is the charge per unit volume. Let's do this again because it's an important law. I equals Q over T, which is N, number of electrons, multiplied by charge of electron over time. We have N, which is number of electron per volume. This is the electron density, okay? Now, instead of N, we can write a capital N multiplied by V. This V is the volume multiplied by charge of electron over time. The volume equals area multiplied by length because the wire is like a cylinder. So this is the cross-sectional area and this is the length of the wire. Now I equal N A L Q E, which is charge of electron over time. Length over time, which is speed. So current equal N, which is charge density, area, speed, which is the drift speed, multiplied by charge of electron. Okay? This expression is very important and you have to understand how to find this value. So I equals N A V Q. Some textbook write in small letter and some textbooks write it capital letter. So you have to understand what is N stands for. We have here an example, a copper wire. This 8.5 multiplies by 10 to the power 8 charge carriers per meter cube, which is the charge density, which is capital N, as we mentioned, or small n. And here the current is given 2 ampere, and this is the cross-sectional area. You have to change this to meter squared by multiply it by 10 to the negative 6, okay? And you can find the value of the current easily, or the speed. The drift speed is very small value. Why? Because the charge, when it is moved through this distance, it will back here and back here in a zigzag motion because of many collisions happen, okay? So the speed or the drift speed, it is very small value. It's about millimeters per second. Now, we have the potential difference expression. We have the voltage. Voltage consists of two forms, potential difference or EMF. What is the difference between these? The potential difference, it is the amount of energy transferred from electrical to other form per unit charge. So, potential difference, it is the amount of energy transferred from electrical to other forms per unit charge. It is energy per unit charge, joule per coulomb, which is equal to volt. Or it is the work done in change the electrical energy to other form, okay? The energy transferred or work done equal potential difference multiplied by charge. What is the definition of 1 volt? 1 volt, it is the potential difference between 2 points such that the energy transferred from electrical to other forms in 1 joule per coulomb. Okay, so this is the potential difference, which is voltage. We can measure the potential difference by insert a voltmeter parallel to the device. Now, we have also the electromotive force, which is the energy supplied by the battery from chemical to electrical energy per unit charge. So the potential difference and EMF have the same definition, but for EMF it is the amount of energy delivered from the battery from chemical to other form. Here from electrical to other form. This is the potential difference. Okay. Now, what is the electrical power? Power, it's known as energy. Power, it's equal to energy over time or work over time. Okay, this is power, energy over time or work over time. Now, the energy or the work, it's charge multiplied by voltage per unit time. Charge per unit time, it is current. So power equals IV. This is the law of power. So power equals I multiplied by V. We can use, instead of V equals IR, depending on Ohm's law. So power equals I squared multiplied by R. So this is a second law for power. And we can use power equal, instead of I, V equals IR, so I equals V over R. I equals V over R. So V over R multiplied by V, power equals V squared over R. So we have this law, or this, and power equals energy over time as well. All of these are equations to find the amount of power, okay? And the power is measured in watt or kilowatt. Now, let's start talking about the resistance. The resistance R of a conductor is defined as the ratio of potential difference across the conductor to the current I. So I take the ratio between voltage to current. I can find the value of the resistance. Now, if we draw the relation between voltage and current, like this, we have here X and Y. Here we have the volts, and here we have the current. So we have a straight line between voltage and current. This line passed through the origin. If we wanted to find the gradient of this line, this gradient equals the amount of resistance. How can I make this experiment? If I bring a battery and a resistor, and we connect a voltmeter parallel to this resistor and a variable resistor attached and a meter here to find the current. So I can find the values or measure the values of current and voltage by changing the value of the variable resistor. So depending on these values, you can draw the value between V, which is the voltage on the y-axis, against current on the x-axis, and this is the relation. So the gradient is resistance. But if you draw current on the y-axis against voltage on the x-axis, so the gradient will be 1 over R, the reciprocal of the resistance. Why? Because V equals I phi R, which is Ohm's law. V in Y equals current on the x-axis, so the gradient is R. Okay? V equals I R, which is Ohm's law. Now, we have resistors follow Ohm's law, and we have resistor not following Ohm's law. Okay? The resistors which follow Ohm's law are directly proportional like this. This is an ohmic resistor, but the resistors which not follow this line, so it is non-ohmic resistors. Okay, so this is an ohmic resistor, this is a non-ohmic resistor. And examples of non-ohmic resistors like the filament lamp, like the diode, thermistor, light-dependent resistors. All of these are non-ohmic resistors because the value is not the same. How can I find the value of the resistance for non-ohmic resistor? To find the resistance at any point, you just take the value of y and x component and v equals I r. So you take the value of potential difference and current from the figure and find the value at that point. Don't try to draw a tangent and find the gradient of the tangent, okay? Now, here we have an ohmic resistor, okay? Ohm's law states that the conductor at constant temperature, the current in the conductor is proportional to potential difference across it. Here we have the diode. The diode allows the current to flow through it at specific voltage. Before that point, the current there's no current pass through it, so it's zero. Which is a backward bias, and at definite voltage it starts to allow the current to move through it. Okay, so the diode is a rectifier. It's allow the current to pass in one direction only. Let's remember this figure from O level. This is the diode, and if we have a current and we have a bulb like this, so the current can pass through here easily, so it is a forward bias, so the bulb will turn on. But if we have, this is the power supply and the diode is connected in the opposite direction, so the current will not pass through this connection, so the bulb will not turn on. This is a backward bias. And you remember very well that the diode can change the alternative current to direct current. How? By allow the current to pass in one direction, just the upper side or lower side. So this is the diode, which is non-ohmic resistor. The resistor depends on the temperature, okay? As we said here, that Ohm's law for a conductor at constant temperature. If there is a change in temperature, and since the resistor depends on the temperature, if it is ohmic or non-ohmic resistor, so you have to be careful of temperature. Okay. Now, the resistance, so it depends on temperature. The resistance depends on the material which is made from. It depends on the cross-sectional area, and it depends on the length of the wire. Okay? Now, if we have a resistance wire like this, this is the length and this is the cross-sectional area. If we have the same wire of the same length but with a larger cross-sectional area, as the area increases, so we have many spaces inside, okay? We have electrons here, and the spaces are more than before, okay? So the current can pass easily through these, not as hard as before, because there are more free space to pass. In the first figure, where the area is smaller, the current will be deflected more than in the larger area, okay? So the resistance inversely proportional to area. As the area increase, the resistance decrease. Okay, now, what about the length? If we have two wires, wire 1 and this is wire 2. If the length increase, the current will move for longer time, for longer distance, so more collisions happened inside. So the resistance is increased as the length increase. Now, resistance directly proportional to length, inversely proportional to area. We can put a constant instead of this, directly proportional. It's equal to some constant. This constant is the resistivity. Resistivity depends on the type of the material and depends on the temperature, okay? Now, resistance equal rho L over A. The resistivity of a material is numerically equal to the resistance between opposite faces of each cable of a cube, of material of unit length in a unit cross-sectional area. Before we finish, the resistance inversely proportional to area. Now, the area of the wire is by r squared. So, if the length double, the resistance double. If the area double, the resistance is 1/2 because it's inversely proportional. If the radius of the wire doubled, the resistance will be 1/4 from its value. Why? Because area equals by r squared. So if the radius doubled, double r, and we have squared value, so it is 4r squared. So we have here 4 times the area, so the resistance will be 1/4 from its value. And if the radius halved, the resistance will be 4 times its value. Why? Because when the radius half, we have squared, so it's 1/4. 1 divided by 1/4, it's equal to 4. Here we have the resistivity of some materials. No need to remember these values. You can see here that the resistivity of semiconductors material is different from those for copper, gold, and aluminum. Okay? You have to remember that the resistivity is larger for insulators because no free electrons inside these materials. In semiconductor, we have some free electrons. In metals, we have plenty of free electrons. Okay? That's all for this chapter. See you later, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.